How's it going, everyone? Welcome to the 11th video. I apologize to the one or two of you who usually watch these on Wednesdays for getting this up a little bit late. But this week we're going to be talking about interactions. We'll load the Tidyverse, LM support, and GG effects libraries. There's also a couple of the one-off libraries, which, just as a reminder, that's when I use the library : and the function, because I don't want to load the whole library because we only use one function from it one time or whatever. But you'll need to install the GG effects package this week, as well as the library's interactions and performance analytics, if you want to be able to go completely through this script. So to look at interactions this week, we're going to look at a health data set where the DV here is physicians is this health measure, which is just some composite score indicating health. Higher numbers indicate better health. We also have how many hours per month the patients exercise and what their age is. So our average age is 39.66. Average exercise is 29.88. Though for the remainder of this video, I will refer to them as just 40 and 30. Just know that that's technically fudging it a little bit, and that actually when we talk about mathematically, when we say the mean, it actually means 39.66. And if you put in 40 where it should be 39.66, those exact values, then there's some rounding issues that can mess things up a little bit. Anyway, point is, I will colloquially call this 40 is the average age, and 30 or about an hour per day is the average exercise. Our participants range in age from 20 to 59. Our exercise ranges from 10 hours per month to 50 hours per month, and our DV, our health scores, range from 13 to 36. If I haven't shown you before, there's a library called Performance Analytics that is mostly useless to you. It's a library that was made for financial analyses, but it has one function called chart correlation that's really nice. So here I'm just calling the data frame that we read in, and I'm leaving off that first column because I don't want subject ID in here. But if you just use this chart.correlation with the capital C on correlation, what it's going to do for you is it's going to give you a really nice, quick, easy way to get your univariate and bivariate distributions and correlations. So when we run that, we can see on the diagonals we have our univariate distribution. So here's our age, here's our exercise, and our health. On the top corners, we have our correlations. So this is negative 0.16 is the correlation between age and exercise. Negative 0.47 is the correlation between health and age, and that is significant. And then 0.73 is the correlation between health and exercise, and that is also significant. Then on the bottom diagonals, or off diagonals, we have all of our bivariate distributions, or scatter plots. So here we have, we can see that when we look at age and exercise, exercise decreases a little bit with age. Same thing with health. Health decreases a little bit with age. And then over here we can see that positive correlation between exercise and health, which is that 0.73, and we can see that here. Anyway, so I like this chart correlation just to get a real quick, easy glance at univariate and bivariate distributions and correlations if you're interested in those. But it's always a good habit to think up front about whether and where to center your predictors. Bill's talked a little bit this week about, especially in this case, if we have age in our model, our intercept, I've said it 1,000 times, our intercept is the predicted outcome when all the predictors are 0. And then our slopes are also interpreted as the slope of whatever parameter when all the other things are 0. And so when you're using linear regression, it's always about what is 0, and an age of 0 just doesn't make any sense. And so in this case, we're going to mean center our variables, which is probably one of the more common things. Let's start with just an additive model, that typical standard multiple regression like we did before the break. And so we want to see if what is the effect of age and exercise on health. So we regress health on age centered and centered exercise. Bill talked a little bit about the getting the terminology here right, and remembering that it's the outcome regressed on the predictors and not the other way around. One thing, if you're struggling with that, one thing that might be helpful, I know I've mentioned before, thinking of this tilde as like what it means, and one of the things that you can say is you could read that as regressed on or is predicted by. So whenever you're writing code, try as often as possible to read things to yourself in plain English. So don't read this as LM data equals DF health tilde age C plus exercise C. Instead, read this as a linear model from the DF data frame, and its health regressed on centered age and centered exercise, or health predicted by centered age and centered exercise. And then just know regressed on and predicted by are synonymous. But at least in English, we read left to right. So when you look at your linear model, you have your left-hand side and your right-hand side. And so if you stop and just think about it, and realize that we write it out in the model, the formula, the same way that we read it out loud. And so it doesn't make any sense. We don't go right to left, so it wouldn't make any sense to say age and exercise regressed on health. That's backwards. That's going right to left. We go left to right. So it's health, your outcome, regressed on or predicted by your predictors. Anyway, so we create this additive model, and then we look at our summary, just like we did last week, and we have our three parameters. The three parameters are the intercept, B0, the slope of age, B1, and the slope of exercise, B2. And so what does B0 represent? Well, that is the predicted outcome, the predicted health score, where everything else in the model is 0, where centered age is 0 and where centered exercise is 0. Well, what does it mean when centered age is 0? Well, that means that for the average age and the average exercise. In other words, we expect if there is a participant in our data set who is 40 years old and exercises 30 hours per month, that's the average age and the average exercise, we predict their health score to be 27.44. Controlling for exercise, we expect that the 41-year-old, so a 1 unit increase in age for each 1 unit increase in age for each 1 additional year beyond that average age of 40, we predict that their health scores will go down by 0.167 points. So if 27.44, if this is our predicted score for somebody who is 40, then for somebody who is 41, our predicted score would be 27.28. For somebody who's 42, it'd be 27.11. Somebody who's 43, it'd be 26.94, etc. All of that conditional on holding exercise constant at its average. So all of that is based on, those are the slopes, the predicted scores for somebody who has the average amount of exercise, that 30 hours per month. And then the same could be said for our exercise, that we predict that holding age constant at its mean, for a 40-year-old who averages 30 hours per month, we predict their health score will be 27.44775. A 40-year-old who averages 31 hours per month, we would predict their health score to be 27.7. For somebody who goes 2 hours above average, so 32 hours of exercise per month, we predict a score of 27.96. So that's all these slopes mean. That just means for a 1 unit increase in this variable, holding the other one at 0, this is what we predict will happen to their scores. So the conclusion that we make from this model is, yeah, unsurprisingly, both age and exercise have significant effects on health of individuals, and that it's a negative relationship with age, that your health decreases with age, unsurprisingly, and that your health increases with exercise. The more you exercise, the healthier you are. So if we wanted to instead look at if exercise moderates the effect of age on health, which is just another way of saying, okay, well, we know it's completely unsurprising, and we know that your health goes down as you get older. But what we want to know is that conditional on the amount that you exercise? So in other words, in plain English, as you get older and age decreases your general health, does exercising more or less change that effect of age, or do you just age? Does your health decrease regardless of how much you exercise? In order to look at that, to answer that question, we have to look at the interaction. And so we're asking, does exercise moderate that effect of age? So to put interactions in your model, a long way of doing it is, as Bill talked about, quite literally creating the product of your two variables. So if we have some data frame and we mutate to create some variable called int var that is just the product of x1 and x2, and then put that in a model with y regressed on x1 plus x2 plus int var, which is, again, just that product term of those two things, that is creating an interactive model. Inside LM, you can use a colon or an asterisk to indicate interactions. The asterisk tells R that you want not only the interaction, but also the main effects of each of the two variables. So x1 asterisk x2 says I want the interaction of x1 and x2 plus the main effect of x1 and the main effect of x2. Whereas a colon says I want the interaction but not the main effects. It will not put the main effects in it for you. So you could either write it as x1 plus x2 plus x1 colon x2, or you could write it as simply y regressed on x1 times x2, and that will also give you x1 plus x2 plus x1 times x2. So in other words, when we look at all of these things, these are all read the exact same way in R. Here we are manually creating, we take our data frame and we create a new variable, age x exercise, which is literally just the product of centered age times centered exercise. Negative 10.7 times negative 19.9 is this. And so we've just created a new variable in our data set called age x exercise. And when we put that into our model and we have our health regressed on centered age plus centered exercise plus the product of centered age and centered exercise, that is the same as if we said health regressed on centered age plus centered exercise plus centered age colon centered exercise, or that interaction of centered age and centered exercise. And that is the exact same in R as just saying health regressed on centered age times centered exercise, where this will, even though we didn't put in the individual effects, because we put in that asterisk, it still gives us those individual effects automatically. And then finally, this last one is the same thing. It's just not with piping. So instead of taking the data frame and piping it into the model and using data equals period for that placeholder, it's instead just saying data equals df. The reason I will always continue to advocate for using piping is because this really makes it a lot easier in the long run. We have not and are not most likely going to unlock like the real power of using pipes in this course. Bill is not interested in making this a R heavy course, but he is far more concerned with you understanding the statistics and kind of conceptual side of things rather than the R side of things. But just for instance, if this was my own research and I get here and I have this model, but then all of a sudden I realize that, oh wait, there's a couple participants who slipped through. This was supposed to be all females in this data set. We were just recruiting females, but somehow a couple males, or perhaps just somebody who identifies as male, or whatever the case may be. We need to take some people out of our model. When it's piped in, it's real easy to come in here and add in our filter, gender equals female, and then add in another pipe, and now our model stays the same. We're not having to go back in and change our data set and go back and rerun things in a whole new way. Using these pipes allows you to chain things together in a way that you cannot do without the pipes, and that really is where the power of the tidyverse, and that's why the tidyverse has become so popular, is because of this method of data manipulation via pipes. Can really change the way that you approach data analysis. But I digress. When we look at our model summary, so this is the model we created, an interactive model of centered age and centered exercise. Now we have a four parameter model. We have our intercept, age, centered age, the slope of centered age, our slope of centered exercise, and the slope of the interaction of the two. So the only new piece of information here is this last one. So what does B0 represent? This intercept? Well, this represents the predicted health score, where everything else in the model is 0. What does that mean? When centered age is 0, when centered exercise is 0, and when the product of centered age and centered exercise is 0. So what does that mean? Well, centered age means for the average age. Centered exercise means for the average exercise. And this product, remember that this is literally just a product. So ask yourself, well, at what point is centered age times centered exercise 0? And well, it has to be when things are 0. And so again, it's when everything is 0. So for the average, for somebody of average age and average exercise, the predicted health outcome is 27.56. Then what does B1 represent? B1 represents holding exercise constant at its mean. A 1 unit increase in age beyond the mean is predicted to decrease that predicted health score by 0.16. So in other words, instead of 27.56, we would predict 27.56 minus 0.1659 for somebody who is 41 years old instead of 40 years old, and for somebody more specifically, somebody who is 41 years old and exercises for 30 hours per month, since that is the average. Same thing here. For exercise, that is just holding age constant at 0, which in this case, holding it constant at its mean. A 1 unit increase in exercise, so exercising 31 hours per month instead of 30, is expected to increase your health score by 0.26, essentially. So this new piece of information then, this B3, what does this represent? What does the slope of your interaction tell you? The slope of your interaction tells you the expected change in slopes of one of your variables with a 1 unit increase in the other. So, in other words, if the expected increase if we expect a decrease of 0.165 or 0.17, we'll call it 0.17. If we expect a decrease in health of 0.17 for somebody who is the average, who exercises on average this much, this 0.004, 0.005 we'll call it, is how much, if we go up 1 year beyond 0, then we expect the exercise effect to change by 0.04. So in other words, if we go up to 41 years old, then instead of our exercise effect being 0.257, it would be this number plus 0.004767. Go up another year in age, then we expect this slope of exercise to go up by that much more. That relationship also goes the other way. That you could say that for somebody of the average age, if we increase exercise by 1 unit, we expect that slope of age to change by 0.004767. If we go up by 1 more unit, 1 more hour on average of exercise, then we would expect that slope of age to change 1 more. In fact, I'm going to skip over this real quick and come back to, because I want to kind of stay on this point here. So if we say, well, what is the predicted exercise effect for somebody who's 55? One way that we can do that is create a new variable. We're simply going to center age on 55. So instead of now the 0 being average, 0 now means somebody who's 55 years old. So we're just subtracting 55 from age and creating the same linear model, regressing health on age 55, where 0, it means somebody who's 55 years old, and centered exercise. And when we look at that, we can see that the expected exercise effect for somebody who's 55 years old is 0.33. You could get this same information based just on the initial interactive model. This is that mod int that we ran, where if we say, okay, well, how many years above 0, how many years above the mean, which is 0, is 55? Well, if we check 55 minus the mean, we are 15.3375 years above the mean. So when we look back at our original model here, and we say, okay, well, for each 1 unit increase above the mean of age, we expect this much of a difference. So if we take that 15.3375 and multiply it by that B3, by the slope of the interaction, we get this 0.07311,386. So now if we take that value, that is the slope of our interaction by this value here, multiplied by how far from the mean, how many units from the mean, from 0 on age, that is, and that gives us this 0.07311,386. So if we take that and add it to our original exercise slope, we get that 0.33. So when we come down here and run this other model, that's where this 0.33 is coming from. It's coming from, well, because our original interactive model says that for each 1 unit increase beyond the 0 of x1, we expect x2, the effect of x2, to change by the amount of that interaction slope. Or you can say that the other way, that for each 1 unit increase in x2, we expect the slope of x1 to change by the amount of that interaction slope. So that is what our interaction slopes tell you. This slope tells you how much does x2, how much does the effect, the slope of x2, how much does that change with a 1 unit increase in x1, or vice versa. How much does a 1 unit increase in x1, what does that do to the slope of x2? Well, you just have to see how many units different is it and multiply that by your slope. So coming back, one common way of interpreting interactions is to center them on interesting or meaningful values. Probably one of the most common ones is looking at like the mean and plus and minus 1 standard deviation. Sometimes you might see like 1.5 standard deviations, whatever the case may be. So here, all I'm doing is I want to find the mean minus the standard deviation of and mean plus standard deviation for exercise. So we know that 30 hours a month is the average exercise. One standard deviation below the mean is somebody who averages 16 hours of exercise per month, and exercising 43.7, we'll call it 44 hours per month, is one standard deviation above. So now I'm just going to create two separate models, and I'm going to center exercise on those two values. So I'm creating a variable called low x and one called high x, and that's exercise. And low x is just centering exercise on that value of 16.05. So that this is now centered on exercise being one standard deviation below the mean. And this one is exercise centered on one standard deviation above the mean of exercise. So this model looks at the effect of age for people who don't exercise a lot. And this model looks at the effective age for people who do exercise a lot. And when we look at them, the plain English interpretation of this is that the effect of age, because now we can look at the effective age for people. Here's the effective age for people who don't exercise a lot. Here's the effective age for people who do exercise a lot. And we can see that the effective age is a lot stronger for people who don't exercise than for people who do. And that makes sense, because here, if for people who don't exercise a lot, that they are below average on the amount of exercise we get, we expect getting older to negatively affect their health more. For people who, so for each year additional of age beyond that mean, we expect their health to decrease by 0.23 points. By contrast, that same age group, going up 1 year in age from 40 to 41, amongst people who exercise a lot, we only expect their health scores to decrease by 0.1 instead of by 0.23. So that's what we mean when we say that the effect of age is weaker for people who exercise a lot, because when you exercise more, your health doesn't deteriorate with age as much. It kind of helps support your age and keep that age from reducing your health scores. You could do this the other way too. That's something that I want to note in these models. The way that you break it down all just depends on which is more interpretively important to you or interesting to you. Because you could have done this the other way. I could have, instead of doing plus and minus one standard deviation of exercise, I could have done plus and minus one standard deviation of age and held exercise constant at its mean, centered. And said high age, the interaction of high age and average exercise, and low age and average exercise. And if we would have done that, then instead of here, our conclusion is the effective age is stronger for people who exercise less than for those who exercise more. If we would have done that the other way and done the plus or minus standard deviation of age and kept exercise centered, then our conclusion would have been the predicted effective age is smaller and weaker for people who exercise more, and stronger for people who exercise less. So it's just flipping those around, but it works the other way. So whether you want to do plus and minus a standard deviation of exercise, or plus or minus a standard deviation of age, depends on, well, which one are you trying to do? Are you trying to see if exercise moderates the effect of age on health, or do you want to see if age moderates the effect of exercise on health? In this case, I would say arguably like it's more likely that this way is going to be more interesting in seeing, does exercise moderate the effect of age, because we can't control age. Age is a constant. Like, you are going to continue aging at the exact same rate from the day you're born until the day you die, quite literally. You cannot change, like, aging, at least not the time of aging, but you can change how much you exercise with that given age. So in this case, what we're looking at is like, all right, so we're holding age constant, and how does so if we exercise more as we age, is that going to be more healthy for us? We can't say, well, if we hold exercise constant, then getting old decreases health. So the solution then is just to stop aging, and then we don't have to worry about exercising. So in this case, conceptually, theoretically, it makes it's more interesting to look at plus and minus the standard deviation of exercise, but just know that could go the other way. So coming back to this, we already looked at what's the predicted exercise effect of someone who's 55, and we saw that you can just center age on 55 and run the model again with that new centered variable, or you can manually compute this way how these things, where that 0.33 point increase came for 55-year-olds. So same thing. Well, what is the expected effective age for somebody who exercises 40 hours per month? And so here again, we're doing the same thing. We're just going to center exercise on 40 and call it X40, and then look at a model with health regressed on centered age and exercise of 40 hours per month, and their interaction. And when we look at that, we see that we have a 0.12 a decrease of 0.12 points in the health scores for each year beyond 40 for somebody who exercises for 40 hours per month. Now, in terms of plotting these, I will show you real quick that there's this this interactions library has a function called interact plot. That I like. This is pretty much literally all I can tell you about it. This is something that Bill had suggested, and I've literally never used this before this week. But basically, you put in whatever your model is, and you can put in whatever your predictor is, and whatever that the moderator is. And so in this case, if we tell it our interactive model and predictor is centered age, and the moderator is exercise. And when we run that, it'll show us, our nice pretty lines. I said that you can flip this around and do it the other way. And so if you wanted to do that and say that the predictor was exercise and the moderator is age, then it will automatically break it down and plot out a mean plus or minus 1 standard deviation. So this model is what we were looking at here when we go back and look at our model summary. So what this tells us, or actually, let's go back and look at our plus and minus 1 standard deviation, which is right here. So our low exercise and high exercise. So the exercise, or this effective age, if we look, we can see for low exercise, that's right here, this light blue dotted line at the bottom, from 0, a 1 unit increase in age drops down 0.23 points. Whereas up here at plus 1 standard deviation, a 1 unit increase in age only drops that 0.1 points. So that's why this line is not as steep as this line, which is what that interaction means. That's why we say that the effect of age is stronger for people who don't exercise as much. Now, this is okay. Oh, and there is also, I'll at least point out, that at least one additional argument that I did see for this interact thing is you can add in plot points equals true if you wanted. And when you do that, it puts in your actual like the actual data instead of just the lines. I'm not a big fan of just lines. It partially depends on the type of research that you do, but at least in my line of research, I can almost always plot the raw data as well as my statistical models, and I always advocate for doing just that whenever it is possible, because then that is the least visually misleading way to represent your data. If somebody can see the raw data and the statistical models, you can see the error as well as the model itself. So, like, as for all intents and purposes, like, you can stop right there with this video. Like, you literally don't have to watch anything else to get all possible points in this class. You will not miss anything. But so down below this, I'm going to show how to do this with ggplot, and I just want to make this absolutely clear that, like, if you can run this line and produce this plot, like, that's all Bill will ever ask from you at most. Like, he is not concerned. He will never ask you to replicate anything that I've done below. Now, you can use what I do below here to make this instead. That's exactly what we're going to do. We're going to remake this plot, but we're going to do it in ggplot, and there's a lot of reasons for that. Now, I have to say, as I was watching Bill's lecture from Wednesday, I got to push back a little bit on all these tweets that he keeps showing about people talking about ggplot and having to Google things a bunch, and the saying that it's a myth that people are able to change their axis labels without Googling it. I'm going to say that's a lie. It is a lie, and I have no problem. I can make some awesome ggplots, and very rarely actually consult Google or documentation for my plots, but that's because I use ggplot a lot. And my point is that if you are making a lot of plots, as I believe you should be, because I believe that fundamentally, you are better able to understand data when you have good visualizations of it, rather than trying to interpret, some numbers that some, algorithm puts out. When you see it, it just makes more sense, and you can intuitively understand it better. So even though Bill doesn't necessarily ask you and specifically tell you, like, create a plot of X, Y, and Z, and like plot this, and create a visualization of this, that should just be part of your data analysis process. When you pull in your variables, you should be looking at those univariate distributions, the bivariate distributions. When you plot your models, you should be looking at your residuals and, like, looking at these models, looking at the data, not just the numbers, because you are going to struggle more to interpret just some numbers on a console, as opposed to when you have a plot and you say, oh, I can literally see the relationship here. So point is that, like, as you use ggplot more and more and more, it becomes second nature. Like, you literally don't have to Google how to add your labels, because you just have to remember there's the one labs function, and the arguments are like x equals whatever, and y equals whatever, and title equals, and subtitle. Like, how hard is it to remember labs? X equals x, y equals y, title equals title. It's not exactly rocket science. And then even as far as what I'll show you down at the very bottom, using like manual things, because people often say, well, what about if I want to change this this legend over here, and I don't want this and I want to change the title, or I want to change the labels, or I want to change the colors, or the line types, or the ... Well, I argue that the easiest way to do it is actually to do it manually, and there's reasons for that I'll talk about. Anyway, point is, what I'm going to cover today is the bare bones way to replicate this graph button ggplot, and then beyond that, I will have a far more complicated plot that is more along the lines of like the kind of thing that I would put in a manuscript, a publication ready plot, as I would call it. So we want to graph the interactive model with age as our focal variable. So in other words, like, we want age to be on the x-axis, and we want to show different models for different values of exercise. We want the mean and plus and minus 1 standard deviation. Excuse me. The first thing that we're going to do is we're going to recreate that model. And I'm going to call it mod plot. It's the same model, except I'm not going to use the centered variables. The reason is that if I could just use mod int as we already have it, but in that case it would be like this, where it would have, our age would be centered on 0 and exercise is also centered on 0. But because I want to see the raw data, I don't want to see somebody with an age of 0, or especially like people with negative ages. I want to see the real ages, and so the model that I'm modeling, I need to have like the actual ages, not those centered variables. So before I showed you how to use predict LM to get the regression lines and confidence intervals, and if we have like a mean and plus and minus a standard deviation, we create a data frame using expand grid where we have like all the values between our min and max age for for exercise that's one standard deviation below the mean at 16.1, and then it also has all those values of age for the average exercise, and then all those values of age for one standard deviation above, and then you pipe that into predict LM, tell it you want confidence intervals, and then you bind it all together, and when you do that, you end up with a data frame that looks something like this. With the fit lower and upper, and then like that's what you pipe into, that's what we piped in to create, our lines and things. But one of the, today instead we're going to use a function called ggpredict, which is from the ggeffects library. ggpredict does the same thing as predict LM, but it does it in one step. You don't have to create this data frame ahead of time. And one of the really great things about it is that it allows you to specify specific values of whatever variables you want just by putting it in brackets here in the terms argument. So here, I just rounded this to 16.1, 29.9, 43.7. I mean, you could call this 44, 30, and 16. That's fine. So all you have to do is use ggpredict, and you put in the model, and so in this case it's this mod plot, the uncentered version, and in terms we use age and exercise, but the specific values of 16.1, 29.9, and 43.7 for exercise. And when we run that, I'm going to store that as a thing called plot df, but I want you to notice here the difference in when you display the object plot df, it displays this way, like almost as if it's like three separate tables. But I don't want you to get confused. That's just because that's how it outputs the object. But if you actually look at it as a tibble or a data frame, you'll see that it's a little bit different, that this like exercise is called group. And age is just called X. Whatever your focal parameter, age is whatever term you put in first, that becomes X. Whatever term you put in after that becomes group. But nonetheless, we have, for 20 years old, here are our predictions for low, average, and high exercise. We predict 28.6, 30.8, and 33.1 as their health scores respectively, with their lower and upper confidence intervals here with conf low and conf high. So then basically what we could do is then take that plot df that we created, and we just tell it that our age equals x equals x because that's our age, y equals predicted because that's our predicted health score, and then we tell it to group and color it by that group variable, which is the exercise, mean plus and minus one standard deviation. And I'm just going to store that as an object called base plot, and then when we run base plot, we can see that that's the same. This is the plot that the interact plot makes. Like at its most basic level, this one geom line argument after using ggpredict to get those predictions for those three levels, this one line here is what will give you that same plot that the interact plot will. If you want to add the confidence interval bands beyond just having like the lines, then you could use geom ribbon just like we did before. So now I'm just taking this base plot that we created right here, and since plot data equals plot df is in the base plot, here where we get below it and we just take base plot and add more to it, we don't have to re-enter data source. So we just take base plot, which is this, and we add a geom ribbon, and I tell it alpha equals 0.3. I'll show you why if you're still not tracking on what alpha means. But now for the geom ribbon, again, x is x because x is that age. Y max is that conf high, which again, let's look at what this looks like as a data frame. So X is that age, so we want our X axis to be X. We want our Y to be the predicted value. Or excuse me, our Y max will be conf high. Our Y min will be conf low. And then our group, again, because we have 3 separate regression lines that we want here, or 3 separate confidence interval ribbons that we want here. So we group it by that grouping variable. And now I created this object called CIs. And when we look at that, we now have confidence intervals around our regression lines. And so as far as what this alpha does, if I just take the alpha out, you can alpha again is transparency. When you're talking about ggplot, alpha is the transparency. And so you know, these are opaque, and if we made the transparency lower actually, then say we made it 0.1, sorry, that should be 0.1, then it'll be super light. If we made it 0.7, it'll be darker but not completely opaque. So that's all the alpha is. And so I usually use an alpha of 0.2 or 0.3 for most things. But anyway, point is that that's how we would add, we can put our confidence intervals based on those regression lines. And then, so looking at these confidence intervals without even looking at the data points, like just looking at these, I hope this makes it clear what it means that there's an interaction and that the effect of exercise differs as a function of age. Because down here for 20-year-olds, there's not all that much of a difference in the predicted score for somebody who exercises on average. It looks like, you know, we'll just call it 31, and then you know, maybe 33 up here and 28, I don't know, down here. But anyway, like these confidence intervals overlap. You can see the overlap in them there. So there's not a significant difference. When you have a 20-year-old, you know, they're going to be pretty healthy, regardless of how much they exercise. That's just how the human body is. By contrast, once you're 60 years old, there's a big difference between people who exercise a lot and who don't. Like, if you don't exercise, you are predicted to have a health score substantially lower than somebody who just who exercises the average amount, or especially somebody who like actually exercises more than average. So that's what this interaction means. The last thing is, if you did want to put your raw data points on top of these plots, you could do that too, just taking this CIs thing that I created here, and I'm going to add geom point, and I'm going to tell it that you know, use the data, the df data frame, and then x equals age and y equals health, and now it will put our actual data points on that plot for us. And if you put all of this together as one, like, this is what it would look like. And the point that I'm trying to make here is, please, please, please do not think that you need to break this down and do this like one piece at a time, and to create an object called base plot and then add your ribbon and create a new object out of that, and then add another piece and create a new object out of that. Like, you don't have to do that. Like, you can just do all of this in one. In fact, like, this is how my plot would look, or how my code would look for this plot. I only did this in this step-by-step fashion just to make it clear what is happening with each step of this code. So please do not think that you have to do this like piece by piece as I did above here. Like, you can just you know, have this portion to create this plot. So that is the most basic and simple thing as far as ggplot way of doing this. And so the final piece then that I really want to emphasize, again, like, you do not have to go below this. I believe very strongly in heavy emphasis in data visualization. Bill disagrees with me, you know, and it's his class by all means. But like, I know that some of you do want to have a taste of a little bit more advanced visualizations and things, and are used generally. So I at least wanted to include a little bit of code down here. And so if we look at this code as a whole, well, let me just run it, and then we'll talk about piece by piece what it does. So we start mostly as we did before. We have our geom line, geom ribbon, and geom point. The only things that I've really changed is I've adjusted the alpha on the ribbon a little bit. I changed the shape of geom point to circle filled, and have these filled circles, and then filled those circles based on exercise. Now the reason I did this is because I used for my line, I used the color argument because I wanted to color these 3 lines. Well, if I used color to color this factor of group, and then also tried to use color as this continuous exercise thing, when I tried to specify what colors, there would be a conflict. So by changing my points to this filled circle, instead of using the color argument, it uses the fill argument. So now I can use color to indicate the mean and plus and minus 1 standard deviation, and then use fill for the circles. Here is just adding on my theme classic, which is my default, to get the white background. For the labels, this is exactly what I'm talking about. That, like, no, you should not have to Google how to how to change your axis labels. Like, it's just the labs. This is just one layer. It's labs, and X equals whatever you want your X to be called, and Y equals whatever you want your Y to be called, and title equals whatever you want your title to be called. And in fact, if you had subtitles, you could say subtitle equals whatever you want it to be, and it would have that as your subtitle now. You could add in your caption. So point is that so now here's your caption, here's your subtitle. Point is that no, you should not have to Google how to adjust your axis labels. That's actually a pretty simple, straightforward thing, and if you're using ggplot, then a lot, then that should be pretty well second nature. Same thing for the scale color manual. Now I've mentioned a couple times the manual, the idea of manual, and so when I said even adjusting your axis or your legend labels and colors and title, all that sort of stuff, like even that can be pretty simple. The reason that I use scale color manual, scale fill, scale shape manual, like anytime I want to specify like these aesthetics, I use the scale blank manual, because then the first argument that goes into that is whatever you want your title to be. So here, instead of exercise, I want it to be exercise with a capital E, and then beneath it I want it to say model in parentheses. So instead of group, I want this to say that it's the exercise model, that because now it's a model for the mean, it's a model for -1 standard deviation, and one for +1 standard deviation. So I can specify, like in the first argument of scale color manual, I specify what I want my legend title to be, the values equals, and I tell it I want it to be red, blue, and green. Red, green, and blue. And then the labels are -1 SD, mean, and +1 SD. So now whenever I run those lines, that's all that's going to do is change here. So now I have my exercise for my models, -1 standard deviation, mean, and +1 standard deviation, and those are red, green, and blue. And it doesn't matter what you put in here. It just, using the scale color manual like really makes it easy to change all of these things. Finally, or not finally, but this scale fill gradient 2 is one thing that like it did take me a while to remember how to do all this. But same thing as far as like giving it a title for my legend, changing this. I just want it to be capitalized. Now, what Scale Fill Gradient 2 does is instead of having a gradient that fades, from dark blue to light blue or whatever, colors you pick and, fade from red to green, I want it to fade from 3 colors. So I want the low to be red, green in the middle, and blue towards the top. So fade from red to green to blue. And then you also have to give it a midpoint argument where you tell it like, well, what is the value of like green? And so it'll automatically like kind of spread itself between the 3 colors. It just needs to know what to set as its midpoint. So I'm telling it that I want the mean of exercise to be the midpoint. So when I do that, I now have this 3-color continuous scale where these low values are red, and then it fades up to green, and then finally up to blue. And so you can see, like, even down here we have like this person, even though like they have the average amount of exercise, like their health is a lot lower than what you'd really expect. And so like using this 3-color fade can help depending on the nature of your variable. Sometimes two color continuous gradient isn't all that helpful, and so using 3 colors like this can be a lot more helpful. And then finally, I just want to center my title, and so to center the title, we just use theme, and I tell it plot title equals element text hjust, which is the horizontal justification, equals 0.5. And so once I add that in there, it centers my title. This is the same, like if you say you did have a caption. So say you did have a caption, for whatever stupid reason, it defaults to the caption going like being right justified. And so if you did have a caption, you'd want to left justify that caption. And so that would be plot.caption equals element text. In your themes, anything that you have, there's tons and tons and tons and tons of arguments that go into theme. And in fact, if you just hover, or actually, let's see if I do. All of these different arguments are all in the theme. So there's tons of things that go in there. So if you're ever trying to change like the tick marks on your plots, anything about like that, the visuals of the plot itself, it's all in here. But anytime you have any of these, it'll be followed by one of these element text, line, grob, rect, etc. So I will concede that dealing with theme here could take a little bit, but once you get the hang of it, it's actually pretty simple and straightforward. But nonetheless, we want our caption to be right justified. So here it's left justified, which means that its hjust is set to 1 by default. If we change that to 0, then that means all the way over to the left. If we put it at 0.5, it's going to put our caption here in the middle. And like I said, I don't know why it defaults to 1, which means that it's all the way over here. But anyway, so we have our caption. We want to change that to 0. It would go over here. Then so when there are multiple things that want to be colored, this is my note where I'm talking about why I changed this to fill instead of color. I will also note that there are times that say you want to do both color and shape by some variable, or in this case, say I wanted to do line type. So now not only do I have different colors for each group, but I also have different line types. But you see how even though it's the same things as this, it gives me two separate legends. Well, another nice thing about the using the manuals is if I take my scale color manual and I make it scale line type manual, because I have the same labels and the same title for the line type legend, it now knows to combine those two things. And so now I have like one is dotted, one is dashed, and one is solid. So instead of it giving me two separate legends, one that's like for the line type that's based on the same three group breakdown, and one for the color, when you use these manual the manual arguments, it combines those legends for you. So that's another nice feature of doing this manually, which is what I advocate for. And so ultimately this is what it would look like. The one thing that I don't really like about this is I typically change my legend position using some type of argument. In this case, this particular graph, there's not really a pretty way to do it. You would need to, but basically you can move this around to try to fill up white space. You could try maybe at the bottom and see what that looks like. And now it puts it down here. There's lots of different things that you can do, but basically I don't like having all this extra white space. This particular graph just doesn't do well for really moving that plot, unfortunately, or that the legend. But anyway, I've been on here long enough, so I will end this video now. But if ever you have questions about how to spruce up your plots a little bit to make them a little bit nicer, feel free to reach out. Like I said, I really can't advocate strongly enough that you do plot a lot, so that you are taking so that you're getting used to all these arguments and making it to where you don't have to Google things every time you use it, and it actually becomes pretty simple and straightforward to use. Also, if you haven't, I would suggest reading Hadley Wickham's paper on the grammar of graphics. I touched on it earlier this semester, but I really can't stress that understanding what the grammar of graphics are and how they relate to one another greatly helps intuitively understanding what all this means. And it's not just a matter of memorizing a bunch of random stuff. There is a intuitive way that all of these different things are connected, and once you understand those grammar of graphics, this all makes sense. Anyway, that wraps up this week's video. Just let me know if you have any questions.